In this video I am going to show you one of my project, that was the project of one subject. The subject is titled as Finite Element Analysis, and I am studying that subject in the first semester of my masters here in JIK, Pakistan. So I have done this project and I have analyzed a quadcopter. So basically what you are seeing on your screen is a quadcopter model, and you can see on its above that we have tested this quadcopter at different frequencies, like that frequency number 52, which is 26 Hz. So it is showing the behavior of that quadcopter at that frequency, or at that frequency of its brushless motors. So today I am going to tell you that how I have done this project, and if you want to do the same thing or something that is similar to it, you can do it by following me. So I have started with the SolidWorks model. So that's the SolidWorks model of the quadcopter. So it is mainly composed of main three components. The one is upper deck, second is lower deck, and then we have from similar forearms. And so that is the arm, and that's the lower deck, and that's the upper deck. I will just tell you a little bit about how I have made this, so that if you want to do the same thing, then you can get some direction. So in order to make that lower deck, you first need to make a sketch for that, just like a sketch I have made here. Let me hide that. So that was the sketch I have made in 2D. So when that was finished, I just extrude it, and that result in the 3D generation of that lower deck. So you can see that here. So it's finished. Then I have made that thing, that is the upper deck, and that was also very simple. I just need to make one sketch for that, and after extruding that sketch, you can get that thing. So it's also very simple. And let me tell you about the that thing, the arm. So here is the arm. You can see that it has some of the details, but it's not very difficult to make. So I have made that thing. It have a little hole, and then it have two spots here and one spot here. That one goes with one goes with the lower deck, and that one goes to the upper deck. And normally in the real quadcopters, there are screws mounted on the lower deck and upper deck, so that all of the arms get fixed in the quadcopter frame. So I have assembled that thing in the quadcopter in the assembly section of that SolidWorks. So you can see that here is the lower deck, here is the upper deck, and then we have a single arm here. Then I have just made a pattern of that and repeat that arm 3 more times. So we are getting here 4 arms. Then because my project was to do the finite element analysis of the quadcopter. So the first part of any finite element analysis is to generate a CAD model for that thing or that system. So the first part have been done. So here is the CAD model, you can see that. Then the second thing is to give it some materials, then meshing it, and then at the last we need to compute the results. So SolidWorks have limitations, or it have a simulation built-in adds-on within it, but because it's a very limited and it's used for low order simulation, so I haven't used the simulation or the finite element analysis add-on which is available in the SolidWorks. I have used another software that is called as Simulink, Comsol Multiphysics. It is a dedicated software for finite element analysis. So let me go to my another PC. So here is the other PC. I am using two PCs here. I am just accessing the second PC from my first PC, because that PC have far more RAM and far more processing power, so it is easy to simulate things and do the FEA of different systems on that thing. So that is the end result, or you can see at frequency number 1, which is 0 Hertz. So this is showing the deformation at when there is no frequency, or it's just meaning that it is at static loading condition. So next plot is at 50 Hertz, means when the motors of that quadcopter is rotating at the frequency of 50 Hertz, then that will be the stress distribution for the quadcopter, and that result was generated for starting from 0 Hertz till going to 5000 Hertz at with the step size of 50 Hertz. So that generated some 101 results, 101. So you can see that at different frequencies it have different stress distribution. So like at a frequency of 150 Hertz, so all of the quadcopter is safe, and there are no a huge amount of stress concentrations in the arms, in the lower deck, in the upper deck. So it is safe at that frequency. Basically my work was to just ensure that my quadcopter, or the quadcopter operating at the frequency that is being used in the quadcopter, is safe. So I have done it for 0 Hertz till 5000 Hertz. So I have found out that there are some frequencies at which the quadcopter just have a lot of stresses, just like yes, you can also see that in this figure, that these two arms are bearing a lot of stress here, while this have some intermediate stress, while that thing don't have any stress. And the lower deck is also experience a lot of stress here, while the upper deck is just I have some stresses in the middle range, but not on the whole. So let me show you that how I have made this thing. So that is the result. First you need to import that Simulink model using that live link. So I have imported from the SolidWorks using that live link. Just click on that and then press OK, which came here. So the CAD model from the SolidWorks will be imported in the Comsol Multiphysics. Then defining the material, I have given it material that have 66 nylon 66, and it have 33% glass filled. So that was material available in material library of Comsol Multiphysics. So I have assigned the whole quadcopter that material. Then moving to solid mechanics, that is you can see that it have just divided the whole quadcopter in 26 pieces. Then I have defined the boundary conditions, some point loading, just like the point loading on the arms, because normally the motors are mounted here, so they are generating the thrust which is in the upward direction. So I have just imitated that thrust by just loading a single point with the force of 18 Newton. That is basically minus 18, because the 18 will be in the downward direction and minus 18 will be in the upward direction, and motors are generally generating a thrust in the upward direction. Then I have just fixed it at the very center, so in order to mimic the project that I am doing in my lab, let me tell you that. So that is my lab, and here I am doing the pitch control of the quadcopter. Basically there are two projects. One was the finite element analysis of quadcopter, and the other is that is my project for one of the other subjects, the advanced system dynamics and control. So in that subject I am just controlling the pitch axis of that quadcopter. So you can see that we have a test rig here, then we have 3 axis gimbal here, and we have fixed the upper deck with that gimbal, so it do not just go upward when the propellers are mounted on it and when the propellers are rotating on it. So in order to just check how the quadcopter behave when I give some input from that PC using the Simulink software. So in order to mimic that, I have just constrained the centers of let me zoom it up some. So you can see two constraints here, one is in the upper deck and one is in the lower deck. Then I have generated the mesh. You can see that because it is a too dense mesh, so it is cannot be easily seen. You can see it, you can see it now. So that's the tetrahedral elements that have been generated throughout the quadcopter. So that was the mesh portion. One thing I want to tell you that it have made approximately 172,000 tetrahedral elements along with 72,000 triangular elements. So where the area was the volume was bigger, so it have made the tetrahedral elements, and in the areas where there was a very low thickness, just like in the upper deck and lower deck, it have just generated triangular elements. You can see that here. So that meshing has been done. I have assigned the material and I have just put on the boundary conditions here. The last step is to compute the results. So after clicking on that compute button, it have taken my time of approximately 1 hour and 27 minutes to just compute all the results, all the deformations, all the stresses, and the result was just shown here. So you can see that in the stress portion we have stress here. So it have generated the stress for all the frequencies ranging from 0 to 5000 at the step of 50 Hertz. So you can see the behavior of that quadcopter under different frequencies. Like you can see that at the 500 Hertz the quadcopter is safe. It don't have any lot of stress concentrations, and it don't have any lot of highly stressed areas. So with increasing the frequency, now you can see that at 850 Hertz the one of the arm of the quadcopter is just under a very high state of stresses, while the other are at the safe region. So we should not operate the quadcopter at 850 Hertz. Moving to some other results. So you can see that the stresses in the quadcopter is a function of its frequencies because of the resonance, because the structure. The quadcopter is also a structure, and every structure have its own mode of vibration, its own resonance frequencies, and when the external frequency or the frequency of the motor just get aligned or matched with the natural frequency of the system, in my case it is a quadcopter, so the system will bear a large amplitude, a large vibration of larger amplitudes, just like as you can see sometimes, just like in that thing. So the whole of the quadcopter is safe, but only the resonance is happening at in the lower deck. So that area of the quadcopter is at the risk now. Maybe it can fail if we operate the quadcopter at 1100 Hertz. So I have exported the results because that was a lot of results. So I have made a GIF file for that thing. Let me show it to you. So here it is. You can see that the frequencies are changing from here, and this is the behavior of quadcopter or the stresses in the quadcopter. So in these areas, in this range of frequencies, the quadcopter is safe. Some standing waves are being produced. You can see that like in that at that frequency you was able to see that the lower deck was just bearing a very high stress. maybe at 4800. Yes, so that's the whole thing. At 50 hertz the whole of the quadcopter bear a lot of stress or is at under high stress condition. And one thing I just want to show you, I have made a little report for my this thing. Is it open? Yes, it is here. So I will attach that report in the description, so if you want to study this project in detail you can just go through that project. So starting with the 2D model and generating the 3D model and applying the boundary conditions, all of the parameters, and these are the results, just like as I have shown here in the results in the initial iteration, because I have done that project for different range of frequencies for different loadings. So in the initial iteration I have done it for a step size of 250 hertz and with the loading of 18 Newton. So you can see that at 1250 hertz it is under a high state of stress, while at 4000 hertz it has some standing waves in it. The same for 4250, and then at 4750 we are having a lot of stress in the lower deck. Then the project I was showing you is covered in the second iteration, moving with the step size of 50 hertz. You can see that at frequency of 1250 hertz it have a lot of stresses in its arm. Then here you can also see that at 2650 hertz again a lot of stresses are produced. The one very good result, or the exact matching of the natural frequency and the rotational velocity or the external frequency just produce that result at 2850 hertz. The whole of the quadcopter, just you can see that what have happened with it, because in the simulations the material is continuous and there is no way that material will break away because of a lot of the constraints. So you can see that there are a lot of deformation have been produced in the quadcopter. So the outcome of that thing is that at 2850 hertz there will be a lot of stresses in the quadcopter. So the quadcopter frame will just tear apart, or it will just break away. So again at 4100 hertz it have that much stress distribution, and 4750 that will be the behavior. So I have concluded the result that we should not operate that quadcopter at 2850 hertz. It is very dangerous for that quadcopter, while some of the other frequencies that I have mentioned here are also dangerous for the quadcopter, and that they can also damage the quadcopter, whole of the quadcopter or some part of the quadcopter, just like the arms or the upper or lower deck or things like that. Then I have just entered the reference here and concluded this project. So I will attach that report. I am not able to attach that file in the description or for the project, because the results were too large and the total file size came out to be 600 MB. So it is not possible to attach that much big file in the description, so I will not attach that. But if you want it, then I can do something for you. I will just upload it in some cloud and then will give you the link. You can download it from here. About the SolidWorks model, again because the file is large, so I will not be able to attach it in the description, but it is here with me. If you want it, you can just comment on it, and I will upload it on the Google Drive or Dropbox, and then will provide you the link. So that was all for my project. So hope so that you have learned something new from that video, and if you are doing the same thing or the similar thing or any project on finite element analysis, then you can just tackle that project or tackle that problem In the same way, you need to first generate the CAD model, just like I have made it here. Then you need to import that model in some simulation software. Then you need to apply the material and then the boundary conditions, and in the last you need to generate the mesh and compute the results. And you are also required to interpret the results, because these are just results. You cannot say anything without having a deep knowledge of what is a stress and why we are using a von Mises stress here, what is the meaning of von Mises stress, why we are using it here. And by the way, I just want to tell you that von Mises stress is a criterion for is a failure criterion for the materials, that von Mises stress show you that when the material will yield, or in our world, in the engineering world, if anything yields, it means the failure. It is just like the yielding of any of the arm of quadcopter will result in the complete failure of the whole quadcopter. So quadcopter will not be able to operate if one of its arm yield, or it just break, or it just fracture. So that was all from my side. If you have any questions, you can ask questions in comments. I will try to answer them. Okay, thank you for watching the video.